Hello, myself Nitin Prakash Rao Patil. I am Assistant Professor in Department of Computer Science, Savitribai Phule University. In this video, we'll be talking about understanding the address computation used by IA32-bit jump instruction while generating the object code. So this I am going to demonstrate through the practical implementation, practical scenarios that I'm going to create in front of you. So as a part of this demonstration, I would be using NASA assembler. Okay, on Ubuntu operating system. Along with this, I'm referring to Intel manual, which would be good helping hand for us. I have added the link here, which can be downloaded. This manual can be downloaded and can be used further. Now, as a part of this whole work that we are going to carry out, our target is to understand when we do talk about jump instruction, how the control gets transferred, no matter whether it is conditional jump or an unconditional jump. Now this control transfer, whenever it happens, that would be either a forward jump or a backward jump. And we are mainly concentrating on the short jumps. Now, whenever we do talk about jump instruction, there is a label, no matter whether you are having conditional jump or an unconditional jump. Now to demonstrate this, I will be referring, as I said earlier, I will be referring to an Intel manual. So let me open that manual. So I'm referring to this particular page now, page number 35 from that manual, which talks about the instruction format for this IA32. So this instruction in IA32-bit or 64-bit is divided into different 6 parts, which talks first about prefixes, opcode, mod, RM byte, SIB, displacement, and immediate. And each one is having some dedicated size. Some of them are optional. Some of them may be required depending upon what kind of operands you are having. Now, when we do talk about jump, actually we are going to move to some particular memory location. So we'll be using this displacement, and this displacement would be 1 byte. And for jump instruction, to differentiate between the kind of jumps, there would be an opcode, dedicated opcode for the same. So let me move to, say, for example, for a while to the jump instruction. So in this manual, for every other instruction, there's an information added. So this particular page talks about unconditional jump, where the address computation, like what are the jump that it may pass the control to. It could be within boundaries, like for example, 8-bit displacement, 16-bit displacement, 32-bit displacement, and so on. Or even in some cases, there would be some 64 indirect addressing would be there. As we are not talking about 64-bit at all, I'm going to concentrate on within a short jump point of view. So relatively, then that address would be within 8-bit. So whenever we do talk about translating the jump instruction, unconditional jump, we are going to see that there would be an opcode used. So as we are going to talk about an address which can be fitted into a byte, so our opcode would be for that jump instruction would be EB. Now when I talk about jump, which is a conditional one, so this is jump if condition is met. So this is JCC it is called. So we know that from Intel perspective, there are multiple instructions added by Intel with respect to the condition codes. So we'll try to make use of probably jump if Z, jump if 0, and jump if not 0. So let me demonstrate this by taking some example. Now for demonstration purpose, I have created a code like this. So I have used syntax of NASM to demonstrate this. So section.text global main, then I am having some statements. Now this program is not going to do anything special, but only our target is to understand how the address would be picked. So I have added JZ for a while, conditional jump, 4 places. The first JZ that I am seeing here would be to considered as a forward jump. And the last 3 jump Z instruction that I have used are considered talking about backward jump. Now for other instructions, what are the instructions that we have added here? I specifically have taken a particular format so as to really make it simple and time bound. Because of the time bound constraints, I'm making it pretty simple. So if you are taking some other instructions, depending upon that size of the opcode and the translation, what are the format that gets generated as an object code for a particular instruction may vary from 2 byte to 4 byte, 3 byte, 4 byte, 5 byte, and so on. So here, what are the instructions that I have taken apart from this jump? Each one would be taking 2 bytes. So for example, this will take 2 bytes, this will take 2 bytes. These three again will be taking 4 will be taking 2 bytes. We have used three labels here: main, LP, and PQR. OK, this LP would be used for backward jump and this PQR would be picked for the forward jump. Now, if I say that, for example, if this instruction get translated, if it takes 2 bytes, then 2, 2, 2. So totally 6 bytes. So ultimately this JZ PQR, after opcode of JZ, it should tell me how many bytes I have to move further. Now, whenever we do talk about backward jump, the backward jump actually goes in the similar way. Only thing is that it stores information in terms of the 2's complement method. Now, if I do say that JZ PQR also would be taking 2 bytes. Okay, JZ LP also would be taking 2 bytes, 2 bytes, but second byte we have to mainly compute in all these 4 cases. So when I do talk about JZ PQR, okay, in place of PQR now I will be seeing 6 return for this forward jump. So if I have one more jump, one more JZ, then ultimately the previous would be having next 2 added there. So we'll take that again as a sample case further with further modification in this code. Now, when I do talk about this, it is going to be 2's complement. So from here, I have to go back. So 2 plus 2 plus 2. So 2 plus 2, 4 plus 2, 6, 8, 10, 12, 14. Correct. So similarly, if I talk about this, 2 plus 2, 4 plus 2, 6, 8, 10, 12, 14, 16. So 14, 16. Okay, kind of. If I talk about this, 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2. So if 1, 2, 3, 4, 5, 6, 7, okay, 4 plus 3, 7, 8, and 9. Correct. So 14, then 16, then 18. So let me first see about this JZ. So if I talk about this JZ, let us see what the opcode is. So JZ related, so relative weight. So this would be short jump. Now if it is 1, then only it is going to jump. So 74. So let me say, let me take this example. So I will start writing this for JZ. So for JZ that would be there. So whatever the code opcode that we said as 74. So it would be 74 and I'm saying 6. OK, because we have to jump further. So this would be for forward jump. Now backward jump, when we computed this. So from here, if I talk 2 plus 2, 4 plus 2, 6, 8, 10, 12, 14. So let me write that 14 in terms of binary. So how do we get it? So 0, 0, 0, 0, 8 plus 4, 8 plus 4, 12, this way. Correct. So 8 plus 4 plus 2, so 14. Now if I compute 1's complement, I would be getting what? 1, 1, 1, 1, 0, 0, 0, 1. Correct. Now if I talk about this JZLP, so 2 plus 2, 4, 6, 8, 10, 12, 14, 16. So subsequently for next JZ, it would be 18. So if I now write 1's complement 0, 0, 0, 0, then 16, 8 plus. OK, now we as it is 16, so it would be having this thing. Correct, as in a binary form. So this would be 16 plus 2. So 0, 0, 1, 0. Now if I take 2's complement of this, what it would be? 1, 1, 1, 0, 1, 1, 1, 1. This case would be 1, 1, 1, 0, 1, 1, 0, 1. Now as I have to compute 2's complement, so if we add plus 1 here, so it should reach to 1, 1, 1, 1, 0, 0, 1, 0. Correct. Similarly here 1 1 1. Now this will become 1 and rest of them will be 0. So with assumption like yeah. Okay. Now next one for 18. So 1 1 1 0 1 1 1 0. Right. So as an a 2's complement perspective. So if I write this, if I separate this, so this would be what? F. Now if I talk about this, if I see whether have I translated 16 properly. So we will compute one more time to demonstrate this. So 2 plus 2 4 plus 2 6 8 10 12 14 and then 16. So 16 we translated to this and then we got 1's complement like this, correct? And then 2's complement we added plus 1 into that and then we get this number. So this would be what? F0. Now next thing like 18, it would be what again? Now it is E. Correct. So now what we should see as a code. So this would be like, for example, 74F2, 74F0 and 74EE. So let us try to translate this code and let us see whether are we getting the similar addresses. So let me translate this. So NASM, I'm taking this LST file. OK, like this. So q.lst. So if you see the first jump that we had 7406, correct? Then next jump that we had was this, which was a backward jump. So 74F2. So we got 74F2. Similarly, next was 74F0, 74F0, and so on. If I go below, this would be 74EE. Correct. Now, even if we make the change here, say for example, if I add one more JZ, suppose JNZ, for example, JNZ PQR. As a sample perspective, if I'm adding only this instruction, so now if I see PQR would be taking 2 plus 2 plus 2. This PQR will be taking second PQR will be taking 6 and this should take 8. So like what we should see in a code is one is 7406. OK, and above that the first would be 7408. So let us see whether are we getting that. Control access. So let us go out. Let us translate this code and let us see what is the file. So you can see 7408 is added for first PQR because 2 bytes are added, and that's how this added. And that is how actually the address calculation will be done. So what we saw here is whenever there is a forward jump, the number of bytes it is going to take further. So it starts from the next line. Wherever the condition, this statement ends, it starts computing from the next line, whatever the number of bytes are. And for backward jump, it computes from the same line. So these 2 bytes, then so on. And then whatever the number that you are getting, it's 2's complement is computed. And then appropriately, the result is resolved. Now internally, this is having some representation where the translation, like the jump would be decided whether it is backward jump or forward jump. Correct. So that is how actually the address calculation can be done. So if you replace JNZ by some other instructions, only opcode would be changing. Rest of the things remain same. Correct. That's what we saw. So if I say, for example, replace that JZ by some other jump, say for example, let me write JNE for each of the cases. So JNE. So what should change is the opcode. It remains same. So now we got 7508, 7506. OK. So this is how we do compute the addresses for the instructions. Thank you very much.